Hello, in today's video, let's discuss a little bit about amplification in MOS amplifiers and look at a specific stage of an amplifier known as the common source. So we'll revisit the operation of the transistor and look at its large and small signal model. We'll then learn about the simple gain stage, which is a common source, and then look at its pros and cons, and then look at the concept of an active load and analyze a circuit with the active load. So let's think about how does a transistor amplify. A MOSFET basically converts any voltage on a gate to a current that flows between the drain and source. So here, if you think about the MOSFET, typically the MOSFET has four terminals. You have a voltage VGS, which is applied when the transistor is turned on, and then you have a current IDS that flows through the transistor. And in the most generic case, this IDS is going to be a function of VGS, VDS, and VBS. Now let's assume that this is an NMOS with VBS equal to 0. Then I can write my IDS purely as a function of VGS and VDS. And so if I assume that the transistor is in saturation, then I have a very simple expression where IDS is proportional to the square of the overdrive voltage, which is VGS minus VT. Right? So the current is proportional to this Kn prime factor, which is nothing but mu and Cox, W by L, or the area, the ratio of the width to length of the transistor, and this overdrive voltage. Additionally, because the transistor in the more generic case has channel length modulation, you have this peak dependence of IDS on VDS. Now again, if you look at a very large channel transistor or a very simple model of a transistor, we can assume that lambda is equal to 0, in which case your IDS is essentially independent of VDS in saturation and is just given by half Kn prime into W by L, Vg minus Vt the whole squared. Now how does this transistor amplify? So let's look at a long channel MOSFET. A long channel MOSFET, if you think about it in saturation, it works like a current source whose current between drain and source, or the two terminals drain and source, is controlled by the voltage that is applied between the gate and source. So if I assume that there's no channel length modulation, then in saturation, the current flowing between these two terminals D and S is independent of the voltage that falls across these two terminals. So I have a current flowing between two terminals which is independent of a voltage across them, and hence I can think of it as a current source. And to ensure that the transistor is in saturation, very simply, we need to ensure that the VDS is greater than the overdrive voltage of the transistor in the NMOS case, or in other words, VDS is greater than VGS minus VT. And if you now think about IDS versus VDS, you see that the IDS follows a dependence on VDS when the transistor is in the non-saturation region, and in saturation, IDS is roughly independent of VDS and hence looks like a current source. Now, what happens in the case of amplification? What happens is you apply a small signal to the gate, in this case a small perturbation in the voltage. When the gate voltage changes, right, and if you assume that the transistor is in saturation, then for small changes in the gate voltage, you are going to get a change in the current which is going to be proportional to the square of the voltage. So you get a change in the drain current. So the MOSFET is converting an voltage applied on its gate to a change in the drain current, and this current can be converted to a voltage if I can flow this current through a resistor. So that's the basic, this is the basic method of building a voltage amplifier using transistors. So very simply, if I think about a small signal, when there is a small change in voltage or a small change in VGS, a small change in IDS is introduced, and this change in IDS is given by Gm times VGS, where Gm is known as the transconductance. This transconductance again is a function of the DC biasing of the transistor, and in the most generic case is dependent on both VGS and VDS. Now again, if you look at the most simple square law model, and if I neglect channel length modulation, I can essentially write the GM in an NMOS to be Kn prime into W by L into VGS minus VT. So for a long channel MOSFET, the transconductance can be controlled by either changing the size of the transistor or by changing the gate source voltage or the overdrive voltage of the transistor. Now let's think about how do we build an amplifier from this NMOS transistor. So here's the very basic common source amplifier, which consists of an NMOS and a resistor, which is connected to the drain of the MOSFET. Now I have three terminals of the MOSFET, right? The source is the common terminal and it's grounded. I apply a voltage between the gate and source so as to create a current that flows through the circuit. And then what I have is I have a voltage that is developed at the drain, right? So now if I assume, so let's first assume that M1 is in saturation. If we do that, then basically what I have is I'm going to get a current that flows in M1, which is going to be some DC current caused because of the bias voltages on the gate and a small current variation because of this small change in the gate to source voltage. So let's assume for now, again, keep life simple. Let's assume lambda 0, there's no channel length modulation. Then essentially in saturation, when my transistor M1 is in saturation, my IDS or the current that flows between the drain and source of the transistor is only a function of the gate to source voltage. So if I think about for the generic voltage that's applied on the gate, which is a sum of a DC voltage and a small AC signal, the current I0, which is the net current flowing in the transistor, is going to be some DC value plus a small change that is corresponding to this change of VI, right? And so we apply the small signal model, and what we have essentially is that IDS is small gm times Vi, as we looked at before. This is the transconductance. Mathematically, what we're saying is that gm is going to be the slope of the function at the DC bias point. So I can write gm as dou f by dou IDS at the bias current. Now let's think about what does it take to keep the transistor in saturation. So remember, this gate voltage is changing. Because of that, the current in the transistor is changing. Because of the fact that the current in the transistor is changing, the current in the resistance RD is changing, which means that the voltage drop across RD is changing, which means that this voltage is also changing. Now, as I told you, we want to keep M1 in saturation. So if we want to keep M1 in saturation, then we need to ensure, right, that M1 always satisfies the saturation condition in that VDS is always greater than VD sat or VG minus VT. So first let's write the KVL in the output loop. So I have VDD is given by IDRD plus this voltage, which is VDS, right? So if I want to look at the VDS voltage or the voltage at the output node, the voltage at the output node is given by VDD minus IDRD. And so if I think about a small change in ID caused because of a small change in the input gate voltage, I'm going to cause a small change across VDS, and that is nothing but VDD minus the net current times RD. In other words, this is DC VDS plus the small response for the input signal, VDD minus IDRD minus IDSRD. And so I have my output voltage or the small change in the output voltage to be minus IDS times RD, right? Or if I write IDS as GM times VI times RD, I essentially have the voltage gain. There is a voltage gain between this small V0 and this small Vi, and it is given by the transconductance times the resistance that's connected in the circuit. So two things to note here. 1, you see the negative sign here. The negative sign indicates that V0 and Vi are out of phase of each other, in the sense that as Vi increases, the net voltage across the drain is going to decrease. Why is that? Because if the net VGS increases, the net current in the transistor increases, which means that the voltage drop across the RD is going to increase, and hence the voltage drop across the drain to source is going to decrease. So as the gate source voltage increases, the drain source voltage decreases, and so you have a relationship where for a positive Vi, you're going to get a negative small V0, and that is this negative sign here. And you see that this gain is very easily controlled by controlling the transconductance of the transistor and the resistance that connected in the circuit. So if I want to design this circuit for any specific gain, I have two design parameters I can play around with. One is the GM and one is the RD. And we know that this GM can be controlled by either by the size of the M1 transistor or by the bias conditions of this M1 transistor. Now, why should the transistor be in saturation? So we see that if the transistor is in saturation, we see that this small signal gain is dependent on the transconductance and the load resistance. And to ensure that this is always true, I need to essentially ensure that at all times, this voltage or the voltage across the drain to source of the transistor is greater than the overdrive voltage of Vi minus Vt. Or in other words, what I get is that my VDS or the DC value of the VDS should be greater than VOV times 1 minus AV into Vi. Right? So what you say is that to ensure that this transistor remains in saturation, there is a certain limit on the drain to source voltage, right? Which means that this configuration restricts the range at the output. Why do I say that? Because if the output signal falls out of the range, then essentially I push this transistor out of saturation. So what that means is with this range being restricted, it means that it puts a restriction on the maximum gain that you can draw out of this circuit. So what happens if the transistor leaves saturation? First thing what happens is you see that because of the fact that the current in the MOSFET, when the MOSFET is in the non-saturation region, is going to be dependent on both VDS and VGS. The system no longer remains a linear system, and you have additional dependencies that fall on the output voltage. So whenever we want to design these amplifiers, we want to ensure that the transistors are always in saturation. And the other important point you want to keep in mind is that because of the imposition that this transistor has to remain in saturation, what we see is that the swing or the voltage range at this node cannot be 0 to VDD. There is no limit on the range at the gate source voltage as long as the transistor is turned on. Whereas what you see on the drain side is the drain voltage can't fall to 0 because that's going to push it out of saturation. So there exists a minimum voltage that needs to fall across the transistor at all times to keep it in saturation, and that is determined by the overdrive voltage. And also because of the fact that whenever we want gain, there needs a DC current that needs to flow in the circuit, which means that there's going to be a finite potential drop across the RD, which means that this voltage can never rise up to VDD. It's always going to be an IDRD away from VDD. So what you see is that even though the input range can swing between 0 and VDD, you see that the output range of this circuit cannot swing from 0 to VDD, but is limited by the choice you made for the overdrive voltage and the choice you made for RD. And let's think about it. For maximum gain, you want a higher GM or a higher RD, right? Higher GM means higher VOV. So what you see here intrinsically, and this is common among most analog circuits, is what you'll see is that the gain is trading off with the output swing. This is known as the output swing or what is the maximum voltage range I can see at the output. So what you see is that if I want to design this circuit for high gain, I'm going to compromise the output swing of the circuit. Another important concept whenever we look at circuits is to talk about what is known as the input and output impedance of the circuit. So in most cases, what we'll do is we'll design blocks, and these blocks are then cascaded together. And so when you connect multiple circuit blocks together, you have to continuously worry about two important things. One, does this block load, the block that you're working on, load the previous block, right? In the sense that, does this cause a huge change in the input characteristics that you're going to have the previous block malfunction? Or the second case, that suppose you've connected another block to this block, can this block that you're designing drive another block that is connected at the output? And so we talk about two parameters when we think about circuit design. One is known as the input impedance, that is, what does the circuit look like when it is connected as a load? Two, the second parameter known as the output impedance, or how much current or voltage can this circuit source at its output nodes. So very basically, if you think about any generic circuit which has an input voltage and an output voltage, it can be modeled using three parameters: Ri, the input resistance; Ro, the output resistance; and Av, the voltage gain of the circuit. Now, how does one measure the input impedance? To measure the input impedance, you open the output node, that is, you set I0 to be 0, and you measure what the input current is for a given input voltage. Now, because the output is essentially 0, whatever is the ratio between the input current and the input voltage is the input resistance. And this is known as the input impedance in the case that you have capacitors or inductors connected. The output resistance is nothing but the Thevenin equivalent resistance seen at the output node. And so what you do in that case is you zero the input. In this case, this is a voltage input. So you apply a zero voltage at the input. You apply a voltage at the input and output and measure the output current, and the ratio of V0 upon I0 gives you R0, right? And very basically what this happens is, because you're shorting Vi to be 0, this dependent voltage source goes to 0, and what you see is that when you apply a voltage at the output, you're going to get a current at the output that is going to be limited by this resistance R0. Now let's calculate the small signal gain. Now that can also be done using the small signal model of the MOSFET. So this is the mid-band small signal model of the MOSFET, which essentially for the NMOS consists of an open circuit between the gate and source. So the small signal voltage that falls across the gate and source is converted to a drain to source current, and that conversion happens through the transconductance of the transistor, and this RO comes out because of the channel length modulation that's present. So to recall, you have Gm given by Kn prime times W by L times VOV, and you have R0 given by 1 plus 1 by lambda ID, where lambda is the channel length modulation parameter. And so if I now want to think about analyzing this circuit, again what I do is I replace this MOSFET with its small signal model, right? So the gate, drain and source are replaced by its small signal model. The input small signal is connected directly to the gate, so Vi is fed directly to the gate input. The output node is connected to RD, and because for small signal this DC voltage is a 0, you essentially have RD connected between V0 and signal ground. And so this is the equivalent circuit that you need to solve to measure the small signal gain of this circuit. And so now again this can be solved very simply by applying KCL and KVL. So first thing we note is that this VGS is nothing but Vi. And if I apply KCL at the output node, what I get is Gm VGS plus V0 by R0 plus V0 by RD. The sum of these three currents should be 0. And if you do the manipulation, what you get is that this gain, or the small signal gain of the circuit, is nothing but V naught by Vi, which is given by minus Gm into Rd parallel R naught. Again, you see here the gain of the circuit is determined by the transconductance of the MOSFET, and it's also determined by the channel length modulation or the R naught of the transistor. So the R naught effectively modulates the load that is connected to the output. Now if I look at the input and output impedances of this circuit, at the input I essentially have an open circuit, which means that there is no input current that is going to flow at the input node, and therefore the input impedance of the circuit is infinity, in the sense that this circuit appears as an open circuit at the input, so it doesn't load anything that's connected prior to it. Now if we look at the output impedance, for the output impedance I short the input and apply V naught and measure the I naught, right? And when I'm shorting V in, essentially VGS goes to 0, so my current source disappears. So all I'm left is with two resistors connected in parallel, and so I get my output resistance to be R naught parallel RD. And so what you see here in this small signal analysis is that this common source amplifier, if it needs a high gain, that is, if you're going to use the R naught parallel RD, which is the large resistance, that also shows as a high output impedance for the circuit. Now, as I mentioned, this circuit configuration is known as the common source amplifier, and it's known as the common source because the source terminal of the MOSFET is common between the input terminal and the output terminal. So the input voltage is applied between the gate and source, and the output voltage is measured between the drain and source of the transistor. Hence, this is known as a common source amplifier. So just like a NMOS, you can also construct a common source amplifier using a PMOS transistor. What happens in that case is, remember, in the PMOS, you apply the highest voltage in the circuit to the source because you want VGS and VDS to be negative. And so the PMOS is connected in this fashion with the source tied to VDD, an input signal applied between the gate and source, and the output voltage collected between the drain and source. And what you see is that here you have the load resistance connected to the drain of the MOSFET. And so if I assume that I have a DC bias VB that is applied to keep the transistor in saturation, I can write IDS in this format. Remember, VTP is a negative quantity, so hence I've done VDD minus VB minus mod VTP the whole squared. And so the overdrive voltage is essentially this term, VDD minus VB minus VTP. And to ensure that the transistor in saturation, again, I need to ensure my VDS is less than VGS plus VTP. Or in other words, when you do the math, you get that the VD or the voltage at this node is less than whatever is the bias voltage at this node plus VTP. Again, remember, VTP is a negative quantity. And so this, as your gate voltage fluctuates, your drain voltage is also going to fluctuate. And you want to ensure that at all times, this condition is satisfied, right? So at all times, the net voltage at the drain has to be less than the voltage on the gate plus a VTP. For the common source PMOS amplifier, again, to do a small signal model, replace the PMOS with its small signal model, again, which consists of a gate. The source is grounded because the source is tied to VDD. The small signal model of the PMOS remains exactly same as the NMOS. You have a VGS that's between gate and source, causing a current to flow from drain to source, which is given by GM VGS, and an R naught that is connected between drain and source. So again, in this case, what we have is V naught upon Vi is minus Gm into RO parallel RD. Now, we have constructed common source amplifiers so far using resistors, right? Now, what is the problem with the resistor? Typically, we don't like resistors because resistors consume a lot of area on silicon. Secondly, they're prone to process variations. So resistors are very unstable. They're prone to process variations. They're prone to temperature changes. Remember, resistance responds very quickly to temperature, right? And the third thing is there is a lot of wafer to wafer variations. So generally we don't like to work with resistors if we can help it. And so we want to basically figure out, is there a way to simulate a resistor using a device that is not a resistor, right? And we know that transistors are the smallest components that can be measured in the fab or can that be fabricated. So can we use a transistor instead of a resistor in the circuit and get the same functionality for small signal? So that is where the concept of an active load comes in. So again, let's go back and visit an NMOS that is biased in saturation. And instead of now applying a voltage at the gate, I apply a voltage at the drain. So in the most generic case, let's assume I have an NMOS. I have the gate tied to a DC voltage. Let's assume the source is 0. And let's assume that I've applied a VDS, right? And let's assume this transistor is in saturation. And what I do now is I apply a small input VDS on top of this DC voltage, and I want to see what the change in the current is. Now, as we looked at earlier in the video, if lambda is 0, that is if this is a perfect square law transistor, you see that the current in this transistor is independent of VDS, right? Or in other words, for small changes in small VDS, IDS is going to be 0. Or in other words, the output resistance of this transistor is infinity. Now, if lambda is greater than 0, if we have channel modulation, I can write my IDS through the transistor in the following fashion. Or in other words, I can write IDS as some I naught. Now, this I naught is nothing but the transistor saturation current without considering channel modulation. And then if I do some math, if I now assume that this VDS is changed by some small value VDS, which impacts the IDS by some small IDS, and what I see is that this small IDS is given by I naught times lambda times VDS. Or in other words, the R naught is given by 1 by lambda ID. So what we see that in small signal, if I keep this NMOS in saturation, then if this node varies, then this NMOS presents a resistance to a small signal which is of the value of R naught when I look from the drain to source, right? So this NMOS in its only when it's in saturation presents a resistance of R naught across the drain and source terminals, and this R naught tends to be high. So now instead of using an RD, we can create the same common source amplifier instead by using a PMOS active load, right? So what we've done is that we've connected a PMOS to the drain of the NMOS. So M1 still remains the same. So this part of the circuit still remains the same. All we have done is instead of the resistor, we've connected a PMOS M2 and we choose VB2 in such a way that the PMOS is always in saturation. Because the two transistors are the only components in the circuit, the bias current must be the same. And so assuming both the transistors are in saturation, so we pick bias voltages such that that is true. I essentially have these two conditions for the drain to source currents in the NMOS and PMOS, and IDSN is equal to IDSP. Now, many a times you'll see that when we do hand calculations, it gets very cumbersome with the channel modulation factors. So for quick and dirty calculations, we neglect channel modulation when we're doing biasing, and we just equate just the currents independent of channel modulation. Please note that we are introducing an error in analysis, but it gives us a good starting point for simulations. Now, as I said, for amplification, we want both the transistors to be in saturation, and which means that if I think about, so if I have to impose the saturation condition, there needs to be a certain minimum voltage that needs to be present across M1. And similarly, there needs to be a certain minimum voltage that needs to be across M2 to keep them in saturation. So I have the two conditions that VD should be greater than VG1 minus VTN and VD should be greater than VG2 minus VTP2. Right? And so this has to be satisfied for all input conditions to ensure that the transistors remain in saturation. So now let's do the small signal analysis. So to do that, what we do again is we replace both the transistors with their small signal models. So here the NMOS is replaced by this VGS1, GM1, VGS1 and RO1. Similarly, the PMOS is replaced by this VGS2, GM2, VGS2 and RO2. Again here what we see is that the PMOS gate is a DC voltage, so it's connected to ground, right? And so all we have left is that, by the way, this current should turn in the opposite direction. So what we have here is a Vi that is imposed on this bottom NMOS transistor. So we have VGS1 is equal to Vi. And if I apply KCL at the output node, what I'm going to get is GM1 times VGS1 plus V0 by R1 plus V0 by R2 should be 0. Again, this current source has gone to 0. Again, please note that the direction of the current is opposite. And so what we get is that AV is given by minus GM1 RO1 parallel RO2. So here if you look at this and compare it to the previous case, in the previous case we had got it as GM times RO parallel RD. So what this PMOS is doing now is this PMOS is acting like an RD, right? And it is giving a resistance of RO2. Please note that this is the small signal resistance. The PMOS by itself is not a resistance, but for small signal analysis, it presents a resistance to the small time varying signal, right? And again, you see here now, because of the fact that this PMOS has a much smaller area, you're going to get better control on the values of R1 and R2. And generally we see that this R1 and R2 can be tuned based on the requirements we need in terms of output swing, in terms of voltage gain, etc. And so the circuit tends to give more flexibility to the designer in designing a common source stage as opposed to the previous RD circuit. Just as we constructed a PMOS with an RD, a similar active loaded PMOS common source amplifier can be constructed where we connect the PMOS. Now this transistor is doing the transconductance because the input signal is given to the gate of the PMOS. And here this NMOS is providing the active load for this particular PMOS. And again here you'll see that the gain is again given by GM1 times R01 parallel R02. So always remember the gain is given by the transconductance of the transistor whose gate is being activated by the input signal, right? So in this circuit it would be the PMOS, in the previous circuit it was the NMOS. And the net load at the output is given by R1 parallel R02. Again here you see that the output resistance of this circuit is going to be R01 parallel R02. So this common source amplifier is a simple configuration for a voltage amplifier where the MOS produces a transconductance and that is generally flowed to a large load to generate an output voltage. The advantage of the common source stage is it provides a very high input impedance. So as an input stage, it's good because it's not going to load the circuit prior to it. However, its drawback is it provides a very high output impedance. So for a voltage amplifier, this is not ideal. Now this idea that you can think about an amplifier is pretty powerful. So we'll come back to this again and again as we do more complicated circuits. That you can think of a MOS network as an effective transconductance. So when you think about an amplifier, you generally think about a network that creates a transconductance and another network that creates a load. And essentially any amplifier can be broken down into a transconductance network and a load network, and the gain can be given by GM times the effective load resistance of the load network. So this we'll invoke very often later as we do complicated circuits.